A question for you. So, which one of the three alcohols, the alcohols on top, would you expect that will be more acidic? So, if we have deprotonation of the first structure here, you will get this. And then, too bad, the oxygen will have to bear the negative charge. We cannot write down any additional resonance structure, and we don't have the help of anything in order to help us with inductive effects, because the hydrogen atom, well, it's not particularly electronegative, right? But in the second structure, there you can see that the fluorine that we have here in the second carbon atom, that will be good, right? Because once I generate my O minus, so then now having an element that is highly electronegative, that will help me to stabilize the conjugate base of that deprotonated alcohol. And in the very last example here, too bad the fluorine is too far away, right? Once I remove the proton from the OH, then the fluorine is way too far to help in any way. So I would expect that the most acidic of all the three structures will be this one here, followed by this one, and this one will be the least acidic. So that will be the one with the highest pKa value. How about the phenols down here? So here we have regular phenol, here we have methyl phenol, and here we have orthofluorophenol. Remember that once we deprotonate the phenol, then we try to write down additional resonance structures, right? There you have. I can bring the negative charge here, and I can localize my pair of electrons on that carbon atom. Or I can do it in the other side as well, right? So there, I can have it in the other side as well. But here, too bad, the methyl group is an electron donor. And so that will destabilize the conjugate base of that phenoxide. So I could expect that the pKa value of this central structure will be slightly higher than the pKa value of regular phenol. And then, on the contrary, when having a fluorine here, fluorine has an inductive effect that will help us to remove charge. So that will be beneficial. And I would expect that the pKa value of the fluorophenol will be lower than the pKa value of regular phenol. Okay, so then now we can move to the preparation of alcohols. By now we have learned already several different ways to prepare alcohols. One of them was in chapter 11. Chapter 11, using the nucleophilic substitution reactions, we can go back and forth from alcohols to alkyl halides. If I want to go from an alkyl halide to an alcohol, what can I do? Well, I can use OH minus as a nucleophile, and I can displace a halogen. I can displace I minus or Br minus, and all those will be possible reactions. And if I want to go from an alcohol to an alkyl halide, what do I need to use? Well, it depends, right? If I want to transform a tertiary alcohol into an alkyl halide, there I can use HBr or HCl, because the formation of a carbocation intermediate will be easy, right? But if I want to transform a secondary or a primary alcohol into the corresponding alkyl halide, in that case, it would be advisable to use a reagent like a thionyl chloride or phosphorus tribromide. The next transformation that we have here between alcohols and esters, that is something that we will explore in greater detail in chapter 21 in the second semester. And so chapter 21, there we will see that that is what I normally call the superstar reaction of chapter 21, which is the Fischer esterification. If you react an alcohol with a carboxylic acid, so in that way you can make an ester. And vice versa, if you have an ester, you can hydrolyze an ester and you can obtain an alcohol and a carboxylic acid. So mechanistic details of that, let's wait until chapter 21. The other thing that we can do, we can go from alcohols to carboxylic acids. Well, obviously, if we have a terminal alcohol like this, I can transform this into the corresponding carboxylic acid. 3 carbon atoms, 1, 2, 3 in the starting material, 3 carbon atoms in the final product, right? But the carboxylic acid is a more highly oxidized species because we are going from 1 bond to an oxygen to 3 bonds to oxygens, right? So that's why that is a more highly oxidized. What kind of reagent would you expect to use in order to oxidize an alcohol to a carboxylic acid? Well, it should be a reagent that will be heavily loaded with oxygen, right? Like a CrO3 or KMnO4 or sodium dichromate, anything like that will be a good guess that will be an oxidizing reagent. Reagents that are heavily loaded with hydrogen, like a sodium borohydride or lithium aluminum hydride, those are reducing reagents, right? So you will never use that for oxidizing an alcohol, right? Transformation of an alcohol into an alkene. Well, you should know that very well, right? So we learned already that a method of preparation of alkenes is by dehydration of an alcohol, right? Dehydration of an alcohol. What kind of a reagent we need for that? You can use sulfuric acid or you can use phosphoric acid. Those are good dehydrating reagents. And then if you want to go from an alkene to an alcohol, well, we have learned at least, we learned 3 different methods for making that transformation. You can hydrate under Markovnikov conditions with mercuric acetate and water, followed by sodium borohydride, or you can use borane followed by hydrogen peroxide, right? By hydrogen peroxide under basic conditions. Then another transformation that will be of interest is the transformation of a secondary alcohol. Let's say that you have isopropanol, that is a secondary alcohol. You can oxidize that to the corresponding ketone, right? So obviously that will be necessary to use an oxidizing reagent. Once again, you can use something like a CrO3. And then if it happens that your alcohol is on the tip of the molecule, so there oxidation of that will give you an aldehyde, right? So there you are oxidizing 1 propanol to propanal, so that is an aldehyde. That is going to be a tricky reaction because typically if you use oxidizing reagents like a CrO3, it will take you in one shot all the way from the primary alcohol all the way to the carboxylic acid. So you will go to the carboxylic acid. But we will learn that there are some special reagents that allow you to stop at the level of the aldehyde. And then transformation of alcohols into ethers. Well, that is the subject of chapter 18. and we will not study chapter 18 this semester. If I have the time, I will give you just a very superficial view of chapter 18, just in case in the second semester you may need that information. And then we have also, okay, so here we have examples of transformation of alkenes into the corresponding alcohols. If you use the non-Markovnikov set of reagents, borane followed by hydrogen peroxide, so that is the reaction 7 that we already learned in preceding chapters. So that will give you the non-Markovnikov addition of water. And if you use mercury salts and water followed by sodium borohydride, so that will give you the Markovnikov product, the more highly substituted alcohol. In the synthesis of diols, this is something that we learned also in previous chapters. So we learned that you can produce diols that they have stereochemistry cis, and you can form the cis diol, or you can form also the trans diol. In order to form the cis diol, you need to use osmium tetroxide in the first step, followed by a reductive step with sodium bisulfide and water. Notice that the configuration of the two chiral carbons, they are R and S configuration. And also you should expect to get the SR configuration. That is not shown. I will show it to you here. The SR will be with the two OHs like that, right? So that will be the SR, and that is the RS. And then if you want to get the SS or the RR, there the way to go it will be by oxidation with peroxy acid. It could be metachloroperoxybenzoic acid, or you can use any other peroxy acid, as Ao shows you. You can use like a CH3COOH, and that is peroxy acetic acid. It works equally well. You form the corresponding epoxide, and then by an acid catalyzed process, acid catalyzed addition of water, and so then you can have the opening of the epoxide and you will get the SS isomer that is shown there, or you can get the RR. I will draw the RR for you here. So the RR will be with this OH down and this OH up, and the methyl group here will be down, right? So that is the RR, this is the SS. All right, so there we have methods for synthesizing diols, alcohols from alkenes, and then in the next mini video, we will get to analyze to discuss the reduction of the carbonyl compounds to produce alcohol.